We now come to the issue of Ampere's law and how we can calculate magnetic fields from current distributions. Now, in reality, okay, Ampere's law very closely mirrors Gauss's law in its utility, in its universalness, but to actually do any calculations, you actually have to have a very high degree of symmetry. So keep that in mind, right? But first things first, if I have a wire, so consider the blue strip there to be a wire, and then a small cross section kind of cut out of the wire for visual purposes. But if this wire is carrying uniform current I in the upward direction here, back in the early 1800s, it was discovered that current carrying wires formed magnetic fields that looped around the wire. Okay, so that's why the magnetic field B here is shown looping around the wire in the direction shown. Now, the direction of the magnetic field is determined by the right-hand rule once again. Okay, but this was done experimentally. So, and actually, as a matter of fact, it was found by accident, as a physics professor was lecturing, and he just happened to have a compass sitting on his desk while he was also doing some demonstrations with circuits, and he noticed that as he would flip switches on and off and establish currents, that the compass needles would deflect, which was very, very curious. And so then he took straight wires and would put compasses around them in a uniform fashion, and he noticed that as the compasses formed a smaller circle around the wire, the deflection was much larger, but uniform. So each compass would deflect the same amount in the same circular direction. And then when you pull the compasses further away, they will get weaker. Okay, so this was an experimentally established idea first, and then it was described mathematically what was going on. So here's what Ampere's law says. Okay, Ampere's law says that the closed integral of the magnetic field around some path length dl is equal to the magnetic constant, or the permeability of free space, times the current enclosed. Now, if you look at this, this looks at first glance not necessarily like Gauss's law. Gauss's law was a surface area integral, a flux integral, and here this is a line integral, right? But the similarities really actually are quite strong. So first things first, this dl here is a path length along an arbitrary loop and we call that loop the Amperian loop. So this is similar to Gauss's law, where your dA was an area element over a surface that we called the Gaussian surface. And in Gauss's law, actually I'll write it down here. So in Gauss's law, you have your electric field dotted into an area element, and your area element or your total surface rather, once it's totally integrated over, is going to enclose some charge. And if it does so, then that charge producing an electric field E, you can calculate that value of E at the boundary of the surface, right? Well, Ampere's law acts very, very similarly. You have this arbitrary loop, okay, so it has to be a closed loop, and that's what the closed sign on the integral says. You have a current carrying distribution. It doesn't have to be inside a wire. It can be a beam of free electrons or protons or something like that. But as long as you have current, if you enclose some of that current with a loop, then you can evaluate the magnetic field at the boundary of that loop. Or let's say at the position of the loop. Okay. Now, once again, it takes to actually do a meaningful calculation. It takes a high degree of symmetry. Okay. So we're going to restrict ourselves to the most basic symmetric situations. But if I consider this wire, okay, and I've got current flowing upward, then this circle represents my Amperian loop. Okay, so that circle represents my Amperian loop, and I've enclosed current I. So I enclose my current through the loop. So the current has to go through the loop. So in that sense, this is not flux, but it's related. Maybe I shouldn't say related. But it's conceptually similar in that the current is flowing through the loop similarly to electric fields flowing through a surface. Okay. So your current has to be flowing inside the loop. Okay, it'll pierce through the area of the loop, if you will, right? And so if under these conditions, then I can evaluate this magnetic field B. Okay. Now, from the Biot-Savart law, we already know that for a single straight wire with uniform current, the magnetic field is given by mu naught I over 2 pi r, right? Where r is the distance from the axis of the wire. So let's see if Ampere's law gives us the exact same result, right? So we're going to have a radius for our Amperian loop of r, okay? And we're enclosing all of the current, okay? And if you have the situation of symmetry where all of your Amperian loop is situated at the same r, which it is in this case, my circle is centered on the central axis of the wire, then B should be the same at all of those points. Okay, so this is the crucial assumption in doing these calculations, very similarly to Gauss's law, where we said that the value of the electric field, if you have a symmetric sphere, everywhere on that sphere, well, if you have a symmetric charge distribution and a sphere encompassing that charge distribution, then like say a point charge, for example, right? So if you have a point charge uh, with a Gaussian sphere enclosing it, and both the point charge and the Gaussian sphere share the origin, then you can say that the electric field is going to be uniform over the surface of that Gaussian sphere. Likewise, we can claim that if our Amperian loop is centered on the axis of our current, then the B field should be uniform across that loop. Okay? So that is the assumption. And what we can do with that now is this. So now we're going to actually do the calculation. Okay? So integral of b dot dl, the closed integral, so this means over the entire path of my Amperian loop, is equal to mu naught times I enclosed. But I'm enclosing my entire current, so I enclosed is equal to I, and B is uniform. Okay? So B dot dl, notice that a little tiny dl, okay, let's use, oh man, I didn't pick my colors very well. Let's use light blue. So dl is also along my Amperian loop, and you'll notice that it is instantaneously parallel with the magnetic field. So that allows us to say that B dot dl is just equal to B dl. Okay? Because they're parallel. And so that means B integral dl equals mu naught I. And the integral of dl across the entire Amperian loop, in this case, since it's a circle, just goes to 2 pi r, because it's the circumference of the loop. Okay, so this becomes b times 2 pi r equals mu naught I, which leads to b equaling mu naught I over 2 pi r. Okay. So we can see that we recover the exact same formula that we did by applying the Biot-Savart law. And if you worked through the Biot-Savart law, you should recognize the utility here. This is a much simpler process. Very similar to Gauss's law, being much similar than the integral for the electric field. Okay. So this is the most basic way to apply Ampere's law, but it is also the most enlightening way to apply Ampere's law. Okay, is for a single uniform wire carrying wire carrying uniform current, in other words. Okay, and then you just enclose all of that current with a circular Amperian loop, center the axis of the wire with the center of the loop, so that everywhere around the loop is the same distance r from the wire, and there you go. Okay, so this is the first application of Ampere's law, right? But this is not the end of the story, okay? This is not the end of the story by any means. So consider a situation like this. I have a battery, a resistor, and a capacitor. Now I'm going to draw this capacitor rather large, so you'll see why here in just a moment. So this is exaggerated, of course, but here's the crucial point. Okay. If let me put a switch in here. Okay. So initially our capacitor is uncharged when the switch is open. And then I'm going to close the switch, right? So we close the switch. And now current will start to flow. Okay? And through the wires, we know what kind of magnetic field we expect. These will be circular around the wire. We just proved that. And if I draw each of these circles with the same size, imagine they're the same size. My artwork is not fantastic, but you get the idea. Even through the resistor, if I measure the magnetic field through the resistor, I get the exact same magnetic field. Okay. And if our current is flowing this way, then the magnetic field is going to be looping around like this. And so on. It'll be looping around like this via the right-hand rule. Okay. So our magnetic field loops around locally. Now, we're not going to worry about the corners. There's some fringe effects and things like that. But where the wire is relatively straight, it'll be like this. Okay. And on this side, our magnetic field will be like this. And so on. Okay? But here's the question. What's going on in between the capacitor plates? Okay? There is no wire connecting the two plates with which to create a steady current, or charging up a capacitor is not going to be a steady current anyway, but there won't be any current between the two plates. Let me not put it there because I'll draw some electric fields here. So this will be true for all time though, okay? I is going to be 0 between the plates. But here's the thing. If I put a magnetometer in between the plates, your magnetometer still reads B. Okay? So what's going on? Well, what is between the plates? Okay? What's between the plates? Well, if this is your positive terminal of your battery, this is your negative terminal of your battery, then what will happen is your plates will gather positive charge on this plate, negative charges on this plate, and you will have electric fields. Okay? But because Q isn't constant and the potential across the plates isn't constant, at least while the plates are charging, that means E is not constant. Oh, nope, that's not correct. Your current is going to be exponentially decaying. Um, it'll start out at your maximum current, and then as the plates charge, it'll die off. Uh, the charge on your plates, though, is going to grow. So, whoops, this is going to be Q equals Q naught, 1 minus e to the negative t over tau. The voltage across the capacitor is going to grow with the charge. Okay? And because, remember that your potential and your electric field are related, okay? Remember that your electric field is the gradient of your potential. Okay? This means that V well, let's put it this way, right? V is equal to ED once this distance has been established, right? So that means E is equal to V over D. So that means that your electric field is equal to V naught over D times 1 minus e to the negative t over tau. Okay? Now, I don't have my vectors here, but that's perfectly fine. The whole point here is that this is a time-varying function. Okay? So your electric field is a time-varying function. And what I can do is draw an Ampere, or not an Amperian loop, but a Gaussian surface. Okay? I can draw a Gaussian surface that encompasses one side of the capacitor. So if I do that, imagine that I draw some sort of sphere. This is a very elongated sphere, but you'll see that there's electric field flux through that sphere. Okay? And so what happens is that because this is time varying and there's a flux, what Ampere discovered, and actually, or not Ampere, but Maxwell, okay, this was actually one of Maxwell's most brilliant contributions to the set of 4 Maxwell's equations, but he realized that a time varying flux of electric field produced a magnetic field. Okay? So what that means is, if I write my flux as phi e to denote that this is electric flux, since it's time varying, we take the time derivative of it, okay? And then we multiply that by the permittivity of free space. This is what Maxwell called the displacement current. And it's a value equal to what the current would be if there were a straight wire through here. Okay? So this current is not from charges moving through wires, but from the changing of an electric flux through some arbitrary surface. Okay? And so this displacement current will have the same instantaneous value as I will through the circuit. Okay, so I'm going to call this ID for displacement current. Okay, and ID has the same instantaneous value as I. Okay, but I is time varying, remember, in the capacitor case. So whatever instantaneous value you have for your current through the circuit, that will be the same instantaneous value as your displacement current, and therefore you will measure the exact same magnetic field strength through here. Okay. Did I draw those correctly? No, I actually got them backwards. Oh, yeah. I drew those backwards. So let me draw them the right way. Yeah, they're going to be going up like this. Okay. So, what that means is that this displacement current will give you the same magnetic field as a current in a wire does. So with that, the entire Maxwell, or not Maxwell, but Ampere's law, can be written as the integral, the closed integral of B dot dl is equal to mu naught times I plus ID. Okay? So, in between the capacitor plates, there is no I, it's just ID. And in the wires, there's no ID, it's just I. And so these terms drop out as necessary, but they're both there when you have capacitors. Okay? They're both not at the same spot when you have capacitors. The current I is running through the wires and the displacement current is between the plates, but they will both exist, I guess, is a better way of saying it. So the complete Maxwell's equation for Ampere's law is given by this. Okay, so this is the complete Maxwell's equation. And remember, your flux for your electric field is just E dot A. So a differential amount of that is your electric field dotted into your differential area element, dA. Okay, so there is the entire Maxwell's equation for Ampere's law with Maxwell's correction. Okay, so this part is Maxwell's correction. Okay, so this is really, really important to note, all right? This is going to become more and more important when we look at Faraday's law, but for the moment, we will leave that there, but we will consider one more fairly in-depth example here. Okay. So I have a wire, and consider this as being an infinite wire. Okay. So it's going to go off to infinity that direction. It's going to go off to infinity in the opposite direction as well. And this will have a radius capital R. And now let's assume that my current density is not uniform. Okay, so let's suppose that I have a current density that looks like this. So what that means is, what this current density would look like, if this is the central axis of the wire, then this lowercase r is my distance from the axis variable, and capital R is my fixed radius of the wire. Okay, so what that means is along the axis there's no current, because along the axis r is equal to 0. Okay, but when I start to move off of the axis, I will get small bits of current, and as I get further from the axis, it'll grow linearly with J naught as the slope. Okay, so my current distribution gets larger as I get toward the surface of my wire. Okay, that's what this particular current distribution is showing you. And let's be very, very formal and define a coordinate system. And let's say this is in the plus x direction. This is the minus x. This is plus y, minus y. Okay. And so my current is moving in the I hat direction. Okay, so J is in the I hat direction. So here's my two questions. Actually, I have three. What is the magnetic field in the region R is less than capital R? B, what is B in region R is greater than R? And then C, we want to show that these are continuous. Okay. All right. So, first things first, remember that I is equal to the integral of j dot dA. Whoop. Okay, so when you have non-uniform current density, this is going to be a bit subtle to handle. Okay, but it's very similar to non-uniform charge distributions from Gauss's law. Okay, the technique is very, very similar. Okay, so first things first, let's just compute what is the total current. Okay, so recognize that dA, a small section of my surface area, dA, okay, is going to be pointing in the I direction as well. Okay, so in this case, dA is equal to magnitude dA times I hat. And my current, right, is acting like this through this surface area element. Okay. But it's also in the I direction. So now we can say that my total current is equal to the integral of J naught R over R I hat dotted into dA I hat. Okay? And then this becomes J naught R over R dA. Okay? But what is dA for the circle? For a circle, your area element dA, if there's no angular dependence, you can go ahead and integrate the angular quantity, and you would get 2 pi. And so the area element for your circle is going to be 2 pi r dr. Okay. And if I integrate this expression from 0 to capital R, I would get pi capital R squared, which is what we want. So this, we know that that's the right element. And so we're going to integrate this J naught R over R 2 pi r dr, and we're going to go over the entire area. So this is going to be from 0 to capital R. Okay. Now, some things are constant. J naught's constant and capital R is constant. And then I have the integral from 0 to capital R of, 2 pi is constant as well. So 2 pi J naught over R. Let's see. So I have R times R dr. So this is going to be R squared dr. And when I integrate that from 0 to R, it becomes R cubed over 3. So this is 2 pi J naught over capital R times capital R cubed over 3. Okay? And that cancels with one of those. And so I have a squared there. Okay? So the final result is 2/3 pi J naught R squared. Okay? So if we knew what J naught was, if we were given what J naught was, then we would be able to calculate the current explicitly. Okay? So this total current calculation is important because we will need to compare some of our future calculations for this problem to that number. Okay? So now for part A. We have current density that looks like this. Okay, and we're going to draw an Amperian loop of radius lowercase r from the central axis. Okay, and so we need to calculate what is the enclosed current. Okay, so we need to calculate what the enclosed current is, right? So our enclosed current can be found from J dot dA, but now where our A is over our Amperian loop, the area of our Amperian loop. Since our Amperian loop is what's capturing the current from 0 to lowercase r. Okay, so this is going to be J naught. I'm already going to go through the dot product because we just did that in the last slide, so we'll skip that step. And so here we have to be very careful, and I'm generally very sloppy with this, so I need to actually do this a little bit better. But you generally don't want your integration variables and your variables that appear in your limits to be the same. So I'm going to generically make these primed. Okay, so we have r prime as our Amperian radius. Okay. And so this is going to be, once again, 2 pi j naught over r. And now we're going to have r squared, r prime squared, dr prime from 0 to r. And so this is going to be 2 pi j naught over r of r prime cubed over 3. Okay? And so what this is showing you, okay, what this is showing you is that your enclosed current is cubic, okay? Your enclosed current is going to be a cubic function of r inside the wire, all right? So now that we have that, now we can plug this into Ampere's law. And we have B dot dl is equal to mu naught times 2 pi j naught over r times, this is not primed anymore. Our integration variable was primed, but our limit was not. So this is now 2/3 pi j naught over r times r lowercase r cubed. Okay, All right. And so now we need to evaluate B along our Amperian loop. Now, as we can see, the magnetic field is going to be looping around this way. Okay. And again, our assumption is if we center the Amperian loop on the axis of the wire, then B should be uniform along that surface or along the boundary of that loop, and therefore B comes out of the integral, and I'm left with dl equals mu naught. Actually, let's write it this way. It's pretty standard to group your constants out front, but it's also pretty standard to write anything in terms of pi and numerical constants first. So 2 pi over 3 mu naught j naught over capital R times r cubed, lowercase r cubed. Okay. And dl is 2 pi r. So the integral, closed integral, dl. So once again, our dl's are along the Amperian loop. Okay. And they are parallel with the magnetic field, which allows the dot product to go to just BDL. And when I integrate around that, I get 2 pi r. So B times 2 pi r is equal to 2 pi over 3 mu naught j over capital R times r cubed. And my 2 pi cancels with 2 pi. My r cancels with one of my r's here. And so at the end of the day, my field is quadratic. Okay? So what this is telling you is that your magnetic field inside the wire grows quadratically. All right? When you have a linear dependency on the distance from the wire for your current. So now part B. Okay, so let's keep this piece in our back pocket here. Now part B, so coming back here, what is the magnetic field in the region R is greater than R? So I have the same thing. Let's draw it a little bit lower than that so we have room for an Amperian loop. So I've got my wire, I've got my current density, but now in the region R is greater than R, I'm going to draw my Amperian loop around the wire. Okay? And my Amperian loop is still going to have a radius R, but now that radius is greater than the radius of the wire. And so okay. And so now my Amperian loop encompasses the entire current. The I total that we calculated right here. Okay. So Now, Ampere's law is actually going to be very easy to apply here. Once again, the assumption is that everywhere on the boundary of that loop will be uniform magnetic field. And the magnetic field will be looping around this way. From the right-hand rule. Okay. And so B.dl is equal to mu naught times my current. The total current was 2/3 pi J naught R squared. Okay. Was there, it was 2/3, yeah, it was 2/3. Okay. And once again, B is going to be uniform. So this goes to integral of dl equals mu naught 2 pi thirds J naught R squared. And B being pulled out of the integral of dl is just going to be now 2 pi r once again. Actually, so yeah, I don't need the prime on this case because I'm not integrating over inside the wire, so I don't need that prime there. And mu naught 2 pi thirds J naught R squared. And once again, the 2 pi's cancel out. And so I'm going to label this B out as mu naught J naught R squared over 3 lowercase r. And so what you can see is that this is a decreasing field. So this is quadratic. And this is inversely decreasing. Okay. Which is what we should get, because for wires we know that the magnetic field goes as a 1 over r dependence, right? We've seen that several times at this point. So this should not be surprising by any stretch of the imagination. So now for part C, show that these are continuous. What this means is that on the boundary of the wire, my magnetic field formulas had better give me the same thing. So what that means is if I look inside the wire and I go from the center of the wire toward the surface of the wire, when I hit the surface, I will get some magnetic field due to this formula. So what this is saying is that B in, when evaluated at the surface, should equal B out when evaluated at the surface. So once again, back to the point I was making just a moment ago, if I start inside the wire and evaluate the field outward toward the surface of the wire, once I get to the surface, I should find the same magnetic field as if I were evaluating the field outside of the wire and moving toward the wire, right? So in one case, I'm inside the wire and I evaluate the field toward the surface. In the next case, I'm looking at the field outside, but I get smaller and smaller radii until I hit the surface. These magnetic fields have to be continuous. There can't be a break at the boundary just because you're at the surface of the wire. That doesn't make any sense. So these formulas had better give me the same thing when I evaluate them at the same point. namely on the surface of the wire. Okay, so let's see what we get. So B in, whoops, as a function of my Amperian loop radius was mu naught J naught over 3 capital R R squared. And B out as a function of my Amperian radius was mu naught J naught R squared over 3 lowercase r. So now if I evaluate this at capital R, this turns into mu naught J naught over 3r times capital R squared. And that cancels, and so this goes to mu naught J naught R over 3. And for my outfield, this becomes mu naught J naught R squared, 3 over capital R. My capital R cancels, my capital R in the denominator cancels with one of the R's in the numerator, and I get mu naught J naught R, capital R, over 3. So these are equivalent. So my field is continuous. Okay, this is a really good check to make sure you got the right answer in both regions. If you don't get that answer, or if you don't find that they're the same, you know something went haywire. Okay, so this is truly important. Okay, but there you have it. The derivation, well, not the derivation, but a justification for Ampere's law, the correction by Maxwell to Ampere's law, and an explicit example using current density with Ampere's law. Okay, so I hope that you have found this video helpful, and we will see you in the next one. Bye-bye.